15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again, and thank you for joining us on this, the 287th episode of Space Nuts. My name's Andrew Dunkley, your host. We talk astronomy, space science, just about anything that people desire, and we get lots of good ideas to discuss from the audience, so thank you for that. Today on the program, we are going to be doing shock, horror, a James Webb Telescope update. Although we're getting a lot of questions about it too, so it's obviously at front of mind at the moment. We're also going to talk about what drives cyclones on Jupiter, and you might be a bit surprised by the answer to that question. And it is thought that there used to be rings around the sun, and that makes me wonder what happened to them. And it also may have resulted in Earth being smaller than it could have been, perhaps. And that cube that the Chinese found on Mars,
Moon,
they finally figured out what it is.
Moon.
It's a real big surprise. Not. Plus some audience questions from James in Cincinnati, go the Bengals, Ralph in Northern California, and Andy in Eastbourne. That's all to come on Space Nuts. My partner in crime is Professor Fred Watson, astronomer at large. Hello, Fred.
Hi, Andrew. How did you know I was a criminal?
I saw your mugshot.
Yes, that's right. Forward and sideways, that's right.
All over Facebook.
Oh, yes.
Yeah. How you been?
Very well, thank you. All good. One slight downer in the Watson family is my younger son, Will, who is now 20, coming up to 26 this year. He's got COVID and he's not very well.
Oh, no.
Yeah, he's languishing, feeling really crook at the moment and having to isolate. And he lives actually in Newcastle, where you used to hang out.
My stomping ground as a kid.
Indeed.
Yeah. Well, we know many people who've got it now. Yeah. It's reached that point where it's not a matter of if you're going to get it, it's when.
When, yeah, exactly.
And we're just pressing on regardless, but I know of half a dozen people in my immediate circle that have got it. So far, so good for me and Jude, but it can't be long. She had 2 staff members out with it. One of the staff members I work with, the Salvation Army office, her husband's got it. Yeah, it's we've been dodging bullets like no one else's business, but you can't dodge them forever, I reckon. Yeah. But the good news is I got my booster yesterday. So,
good. Yes.
Yeah, that's done.
Yeah.
No side effects either. Oh, maybe just a little bit of fatigue, but nothing significant. Got the Pfizer dose this time because I got AstraZeneca the first time. So
that's the same with me. That's exactly what happened. And I had no side effects either from any of them, in fact. I've been very lucky.
I got to tell you, though, they released a study, a month or so ago to say that they've discovered that AstraZeneca is the vaccine that keeps more people out of hospital than the others.
There you go. There you go.
Oh, dear. Anyway, I'm happy to get anything.
Yes.
That's where I'm at.
Yeah.
Enough of COVID. I think we've, spent 2 years talking about that, and it's not over yet. But let's get on to our first topic, Fred, and that is the latest update on the James Webb Telescope. I saw some recent reports to say that all is going well. Things are unfolding and unfurling, and it's going along nicely. I've seen some great astrophotography too. A few people have actually picked up images of it, which is quite astounding.
Okay, no, I haven't seen that. Do they have any detail in them, or is it just a point of light?
It's just a streak of light.
Yeah. That's what you'd expect. It's not big enough, really, for a small telescope to resolve it into a shape. You can do that with the International Space Station, but of course that's only 400 kilometers away. So, anyway, you're right. The news is all good coming out of the Space Telescope. Sorry, the James Webb Space Telescope. The big news, of course, is that everything that was supposed to unfurl has done. And the latest thing was the last portion of the mirror. Remember, it's in 18 segments, but it basically was in 3 parts with a central section and of I think 12 segments, and then 2 3-segment sectors on the outside that unfolded and locked into shape. Of course, they still haven't turned that array of mirror segments into a contiguous optical surface yet. That's for the future. They've got another almost 6 months before we expect, in fact, more like 5 months before we expect to see any images from it. So there's a long way to go still. But the telescope is in good shape. There was a really nice comment from Thomas Zurbuchen, who's chief of NASA's science missions. He said, "We have deployed the telescope on orbit, a magnificent telescope the likes of which the world has never seen." He was talking to the team that did it, and he said to them, "So how does it feel to make history, everybody? You just did it." I love that, and it is. It's a big step, and it's fantastic news. The telescope is well over halfway to its Lagrange point. It's more than 1 million kilometers away. It's probably significantly more than that now. That was where it was a couple of days ago. So really, very, very, very good. Very good news coming out of the Webb. And let's keep our fingers crossed that all will continue to be well.
Yes. How quickly do signals and instructions to and from the James Webb Telescope take once it's reached its destination? It wouldn't be that long, would it?
It's not that. No, it's not. 1.5 million kilometers divide by 300,000. It's an easy calculation. It's got a 5 in it somewhere in the answer. So 300,000, is it 50 seconds? That might be right.
Okay, I'll take your word for it.
No, it can't be 50. It's 5 seconds. That's the answer.
I'm just doing it now.
Thank you. Yes, it's 5 seconds.
5 seconds.
Each way.
Nice work. Oh, that's good, isn't it?
Yeah.
I did hear a news report only this morning that they reckon it's got enough fuel to work for 20 years.
Yeah, that's right. Keeping it on station, principally.
Yeah, exactly. Okay, well, we'll probably have another update for you next week. I think the scariest part's over, but there's still a bit to do, so don't count any chickens.
No, that's right. There's always the unexpected.
Yep.
Yeah. In fact, they've already experienced the unexpected when I think we might have mentioned this last week.
Heating motors.
The overheating motors, yes,
Yeah.
when they've stretched the heat shield or the sun shield.
Mm.
Anyway, that all got cured by taking them out of the sunlight, and it's all fixed.
Indeed. Okay, let's move on to our next story. And this is one that has been published, a new study into what might be driving the cyclones on Jupiter. For those who have no idea what I'm talking about, some people call them typhoons, some people call them hurricanes.
Yes.
We call them cyclones in Australia. And it's an interesting development in terms of what they've come up with, because what drives cyclones and typhoons and hurricanes on Earth is the oceans. There are no oceans on Jupiter, but they think it's pretty much the same kind of thing.
Yes, that's right. It is. It's an amazing story, this. And I guess to some extent you could lead your thinking in this direction simply by looking at some of the photographs or some of the images of Jupiter's cloud belts that have come back from the Juno spacecraft, because that's what's really driven this realization. Juno, NASA spacecraft in orbit around Jupiter, in an orbit that actually carries it within Jupiter's radiation belts briefly, which meant that all the electronics had to be specially shielded. But Juno's been doing a fabulous job. I can't remember when it went into orbit. It's a few years ago now. But the images that come back show the structure in these cyclones. The structure around the Great Red Spot, which itself is a cyclone, but other smaller features. And in particular, the way you can see the way these circulate, these spinning fragments of atmosphere with their different coloration, how they sort of drag the other atmospheric features around with them and cause these eddies around the edges of them. And it was as you said, oceanography. It was a physical oceanographer by the name of Leah Siegelman, who is at the Scripps Institution for Oceanography, well-known oceanography institution at the University of California, San Diego. And Leah looked at this and thought, wait a minute, this atmosphere is behaving like an ocean. And, it's basically what she's done is looked at the images in close detail and bringing to bear the physical principles that are used in what's called geophysical fluid dynamics, the way fluids work on the Earth.
Yeah.
And basically has come up with evidence for something called moist convection as being the driving force for these phenomena. Moist convection is essentially when hot air rises. It's convection. That's exactly what it is. It's warmer air rising, but of course there's moisture in it as well. And there's a nice quote from Leah. She says, "When I saw the richness of the turbulence around the Jovian cyclones, with all the filaments and smaller eddies, it reminded me of the turbulence you see in the ocean around eddies. They are especially evident on high-resolution satellite images of plankton blooms, for example." So, we've got images that look similar, but caused by an entirely different, not entirely different physical process, but entirely different phenomena that reveal the images. It's the coloration of the eddies caused by different materials within Jupiter's atmosphere that gives you the impression of these things on Jupiter, and plankton blooms on the Earth. But what's driving them, the underlying physical mechanisms, are common. And in fact, it's got it's got some neat outcomes, because we understand the Earth's ocean better than we understand the atmosphere of Jupiter. And you might be able to draw conclusions from the way the Earth's ocean behaves and actually test that on the atmosphere of Jupiter, whether you've got similar phenomena. As she says, once again, this is Leah, to be able to study a planet that is so far away and find physics that apply there is fascinating. It begs the question, do these processes also hold true for our own blue dot? So you can do it both ways. You can look at, the phenomena on Jupiter and draw conclusions for that and say, does this work on Earth? So a very nice piece of work, very nice indeed.
Yeah, for sure. And in answer to your question, the Juno space probe went into orbit around Jupiter in July of 2016, the 4th of July.
Yeah, it's amazing. So it's, 5.5 years already.
Yeah,
feels like a couple of weeks, Andrew.
What was the length of that mission supposed to be? Do we know?
Yes, it was very well planned. Actually, I think they're still on schedule with it. I do remember that looking at the mission profile, because I think as the mission goes further on, they get the orbit changes. There's a lot of orbit changes for the spacecraft. And they probably take the higher risk things like plunging deeper into Jupiter's magnetosphere later in the mission, when you've got some good data from the beginning. A bit like Cassini, which flew between Saturn's rings and the planet right at the end of its mission.
Yeah, took a big punt, and if it all came to nothing, what we wanted. But
yeah, that's right. So yes, so I'm not sure of the answer to that, but we can certainly check up and find out. But I do remember it was very well, is well documented what was going to happen.
Yeah, I think I've said before, it must be exciting to be on one of these mission teams. Juno got a lot of attention when it first started, and what was it, 5 years it took to get there or something? And these people are still working. They're still, it's not a matter of, okay, it's got there and it's going around taking pretty pictures. People are still working the project.
Yeah.
And it'll be the same with James Webb. It'll be the same, any kind of mission like that. There are control rooms all over the place where people turn up every day to
Yes,
do what they need
that's right.
to do to get the data and learn everything they possibly can about these strange worlds that we're so close to on a universal scale.
What a job. And for many people, that's a lifetime's work because they're probably involved with the mission planning, 10, 20 years before the mission flies. I remember talking to Linda Spilker, who was the project scientist for Cassini. She came out to Australia a couple of years ago, and we looked after her here because she gave a lecture for us, the Alison Levick lecture. And she said it was her entire career, basically. And she's a very mature scientist. She's not, she's still working and still doing great stuff. But she's not in her 20s anymore, if I can put it that way, and neither am I. And she said it's her entire career, and she's still going strong with possible future missions to Saturn. So long may it continue.
Yes, indeed. Fantastic. All right. We will obviously, there might be more to tell in regard to
I think so.
Mission going forward too.
Indeed, there might.
And you'll hear it probably first or 50th here on Space Nuts. Oh dear. We'll take a break. You're with Andrew Dunkley and Fred Watson.
0G, and I feel fine.
Space Nuts.
Now, if you're a social media follower, we are on social media, and we have thousands of people that are following us on Facebook, whether it's the official Space Nuts Facebook page or the user-created Facebook page, which is the Space Nuts Podcast Group Facebook page, where you can all talk to each other, ask each other questions, upload your pictures. A lot of people do that. Sandy in Melbourne has been publishing a lot of his astro photographs, and I've got to send Sandy a shout out and a thank you, because he's been helping me with this little baby here to get my astrophotography kick-started. So I really do appreciate what he's been doing. So thanks, Sandy. But yes, if you would like to get onto social media and find us, you can do a search in your Facebook search engine for Space Nuts or Space Nuts Podcast Group. We're also on Instagram. Spacenuts.io is our username, and our numbers are pushing on towards about 200 followers now. So it's growing really fast. And we appreciate that. Yes, thank you for chasing us up or following us on Facebook. And we occasionally get questions through social media as well. And that's lovely. Now, Fred, what's this thing about Earth being smaller than it could have been because there may have been rings around the sun that stopped a super Earth from being born? This is very, very strange. And I'm guessing we're talking pre-planets, the very, very early stages of the solar system.
We are, yes. So we're talking about the time when the sun was a newborn star. It was surrounded by a protoplanetary disk, which is a disk of dust and gas, which is very turbulent and in which the planets form. And we know these things exist, or we know that the sun had one of these disks around it because we see them around other stars, around young stars. And as I said, they're called protoplanetary disks. But there's interesting details in this. Now, when we know much more about the origin of the solar system by looking at the way other solar systems have evolved. And now we've got this almost an industry of discovering the planets of other stars. We can look at these distant solar systems and compare them with our own. And that is the basis of this work, which has been carried out by scientists, one of whom at least is at Rice University, which is in Houston, in Texas. Actually, I think he is the lead author, Andre Isidoro. And what they posed the question, in fact, I can quote Andre exactly on this. It's always nice to be able to quote these scientists saying what they've actually said. He says, if super Earths are super common, because that's what we found pretty well in our investigations of other solar systems, if super Earths are super common, why don't we have one in the solar system? And that's a brilliant question. If other solar systems frequently have these planets which are about twice the size, the diameter of the Earth, up to 10 times the mass of the Earth, what we call a super Earth, if they are as common as they seem to be, why haven't we got one? What we've got is, of course, the ice giants, Neptune and Uranus, which are rather bigger than that. They're not what you'd call super, you wouldn't call them super Earths. They're too big, and they were formed out in the depths of the solar system, whereas the rocky planets were all formed in the inner region of the solar system. And that's actually the clue to why the solar system doesn't have one of these, that Andre Isidoro and his team have actually uncovered. So they've done all kinds of modeling of what the early solar system was like. And it comes down to something that I think you and I have spoken about before. I certainly wrote about this in Spacewalk because it's such an interesting idea. The idea of these frost lines, or sometimes called snow lines.
Yes.
Which is where the distance from a star, where, for example, where water turns from a vapor into ice, basically, that will be called a water snow line. So this, and actually, the neat thing is the water snow line is, if I remember rightly, it's somewhere between the orbits of Mars and Jupiter today. But it may not have been like that in the early solar system. I think these things were closer in the early solar system. Anyway, you don't just have water that produces a snow line. Further out, there is a carbon monoxide snow line where carbon monoxide becomes an ice rather than a vapor. Excuse me. Carbon monoxide, of course, found in comets. Comets are made of ices, and CO ice is one of them. But there's also further in towards the sun, where the temperature is hotter, and certainly in the young sun's period it was. I think I've got that the wrong way around. Actually, I think the young sun was cooler than the present day sun, which is why these lines are closer in to the sun rather than further out.
Yeah.
Sorry for the confusion there. But anyway, further in, when you get nearer to the young sun, you come to a line which you could still call a snow line, but it's kind of not really anything to do with snow. This is where the silicates, where the rocky stuff actually turns into a solid material rather than being a vapor. And it's sometimes called the silicate sublimation line. Sublimation is when something turns from a solid into a gas. And so if you go nearer than that, you've got a gas. The silicate's a gas rather than solid. So what you've got is all these regions where there's this key transition from a vapor to a solid for different materials. And it turns out that you get planetesimals forming in those regions. These are the things that are the rudimentary building blocks of planets. And the theory that these people, this group at Rice University, have developed is that because you've got these regions where the planetesimals are more common, you get essentially what they call pressure bumps. Regions where the dust and material is concentrated, and that actually itself generates the planetesimals because of the sublimation features. So what Dr. Isidoro says is our model shows pressure bumps can concentrate dust, and moving pressure bumps can act as planetesimal factories. So the two go together. The pressure bumps regulated how much material was available to form planets in the inner solar system. And so what they're suggesting is that it's this regulatory attribute of the pressure bumps that stops the Earth turning into a super Earth. I'm not really explaining this very well. They said it's basically the way these rings form dictate what size planets you get, and they suggest that this comes from their computer simulations, that if at least one of these rings of planetesimals was delayed, if it formed later, in the solar system's history, then you might have got super Earths rather than just standard Earths. Dr. Isidoro made a comment. By the time the pressure bump formed in those cases, this is in the sort of inner planet region of the solar system. By the time the pressure bump formed in those cases, a lot of mass had already invaded the inner system and was available to make super Earths. So by the time when this middle pressure bump formed might be a key aspect of the solar system. In other words, had that been delayed, the super Earths might, because there was mass available to make super Earths, had that pressure bump been delayed in its formation, you might have got super Earths, but you didn't because it wasn't delayed. Right. I'm sorry, I haven't really explained that very well, Andrew.
It all came down to the timing.
It's the timing, that's right, exactly so. But a really interesting study, and one, for any listeners who want to follow it up, there's plenty of detail on the web. I've been looking.
It's in Nature Astronomy, I think.
That's where it's published. That's right. Yeah. I've been looking at the Science Alert page, which is always worth a look. It's a good news site. Yeah.
All right. Here's a question for you then.
All right.
Let's assume for a moment that the conditions and timing were right to create a super Earth, and that this planet became a super Earth in its early days. What would that have meant for us?
Yeah, we'd have been super Earthlings. So rather than just standard Earthlings, we'd have been super. I don't know. Well, we might have been, this is a bigger planet we're talking about, 10 times the mass of the Earth, significantly greater gravitational pull. Who knows how we might have evolved, but it could have had life evolved and developed to the stage that it has now on planet Earth. Who knows what we might have been like? We would certainly have been very different.
Bigger?
Yeah, I think we'd have been bigger. We'd have had to be beefier. With solid, big boned. We'd have been big boned. Oh, yes. That's the word.
Not fat. I'm just big boned.
Yeah, because you'd have needed the strength of those bones to, put up with the increased gravity. So your bones might have been made of something else other than calcium and things of that sort.
It's interesting to think about, isn't it?
It is. Yes, there's a science fiction story in that for you, Andrew.
There probably is. There probably is. Although in the Turanian enigma, there is a species that have those kinds of characteristics.
A big boned.
Yep.
Yeah.
Yes, but for a different reason. But I went that way. Yeah. Maybe I should have thought of a super Earth, but anyway, doesn't matter.
It's a nice story.
For another one, another story one day. No, but it's fascinating. So we are what we are because of just the freak of timing.
Maybe that's right. Yes, maybe that's right.
Fascinating. All right, that is where we'll leave the sun and its rings and the not super Earth that we live on, and move over to the greatest mystery in human history, and that is the cube that they found on the moon when the Chinese U-2 rover sort of pointed its camera and went, "Oh, look, it's a box." They've found out what it is, Fred. I'm very excited to learn the answer to this question. As you can see, I am just over the moon.
Yeah. Oh, you should be on the radio. It's a rock.
Of course it's a rock. What else was it going to be?
It's always a rock, isn't it? I mean, it's the age-old issue of pareidolia, where we see things that look like something else. And, of course, Mars has been the place where most of these things have come from. I made a list a few years ago for a talk of all the different things that have been seen on Mars, from witches' hats to top hats. Truck tires. There was a truck tire found on Mars. There's a grey ghostly lady who never seems to move. She's been found on Mars. Yeah. But they're all rocks.
It's funny. You what's it called? Pareidolia?
Pareidolia. That's right.
Yeah, where you try to create. Yeah. You see something and you give it a life image.
Yes, we make it into something that's familiar.
Yeah, that happened to me this morning. I was on the way to the radio station before my breakfast shift, and the sun was already coming up, so there was a bit of light. And I saw something ahead of me, and I thought, "Oh, that's a dead rat, for sure." No, it was just a piece of tyre rubber.
Yeah.
But
Yeah,
my
yeah,
brain interpreted
yeah.
a
That's
dead
right.
rat. Yeah.
I've swerved for dark patches, just a bit of dark bitumen on the road that you think is a kangaroo.
Yeah.
It's exactly the same thing. That's right.
Yeah, you don't want to hit one of those things.
Oh no,
Yeah,
no, no,
they are.
no.
Speaking of big boned, you do not want to hit.
No, exactly. Many times I've had accidents like that, which are always very, very distressing for
Yeah,
everybody concerned. Yes,
they certainly can destroy a car. And
indeed.
yeah. All
So
right.
anyway, nothing like that on the moon, and not even a cube. Actually, the Chinese people commentating on it in China, they nicknamed it the Mystery Hut. They thought it looked like a bit of a house or an enclosure.
Right.
But in fact, the pareidolia has continued because what they did was take the rover, which is called U2. It's U2-2 actually. This one, because U2-1 was on the near side of the moon, and U2 is the jade rabbit. That's what its name means in Chinese in China. But the first person to see this rock in a bit more detail, apparently, thought it looked like a jade rabbit. It's a rabbit. It says that it's the Chinese Aerospace website has a journal on driving a driving diary for U2 number 2, and one of the comments is the drivers were a little disappointed that this was a rock, but just as everyone was lost, the driver stared at the enlarged picture and covered his mouth and exclaimed, "Gosh, this is U2." So it's now the rock is being called Jade Rabbit because that's what U2 means.
Okay. Well, I had two theories. It was going to be a rock, or it was going to be my missing Amazon delivery.
Right, yeah.
But that's okay, because Jeff offered to go and get it for me.
Good on you, Jeff. Yeah.
All right, but it's just a rock. So
it's
very
just
disappointing.
Yeah.
As they all turn out to be. This is Space Nuts with Andrew Dunkley and Fred Watson.
Space Nuts.
Now, we've been telling you about Patreon and Supercast for quite a while. If you want to become a contributor to the show on a regular monthly basis, you choose how much you want to spend to contribute to Space Nuts. We recently told you about the option to buy us a cup of coffee. There is a buy us a cup of coffee button for a one-off donation to Space Nuts, and a lot of people have taken up that offer. So thank you, we appreciate it. One person, Fred, has done it literally.
Oh yes, that's right.
We've got a Starbucks voucher.
Good on you.
And I'd like to send a big shout out and thank you to Marie Claire in, I'm going to assume, Miami this time of year, where she's based. For sending us, literally sending us coffee. So thank you for that. I don't know how we're going to split that 3 ways, but
no, that's all right. We'll work it out.
And you can watch. That'll work. Okay. Now let's go to our questions. We've got 3 questions today. One of them's a real quick one, so we're going to throw in that one at the end. But we'll go firstly to Cincinnati. James.
Hello, Mr. Dunkley and Professor Watson. James from Cincinnati, USA. Mr. Dunkley, the last time we spoke, you said I had a great radio voice. Thank you for that. I'll have you know I also have a face for radio.
Me too.
On to my question. Many of Hubble's greatest discoveries were unplanned and unexpected from its primary mission. What unplanned and unexpected discoveries are you hoping James Webb Space Telescope will uncover that are not part of its primary mission? Thanks, guys. Have a great day.
Thank you, James. We don't know because they're unplanned.
Yes, that's right. It's a great question, and it's actually it's not just airy fairy stuff. This one of the points that is always made when you make the case to build a new facility in astronomy. What you do is you write effectively a business case as to what this new, whatever gizmo it is, whether it's ALMA or the Very Large Telescope or James Webb or whatever it is, you build a science case for it. So what science are you going to push forward? What are you going to discover, particularly to study using this new facility? And the James Webb telescope, of course, is many, many different things, including the first stars and galaxies, which is an incredible thing to be looking out for. And at the other end of the scale, the atmospheres of nearby exoplanets, being able to analyze what's in the atmospheres of the planets of other stars. All of those things go into the science case. But the point is always made that with every new facility that's ever been built in astronomy, it's been the unexpected that has really often changed the direction of science. It's the kind of thing that really you couldn't think of. I mean, people do think of these things, and scientists certainly think way outside the box. Oh, what if we found X or Y? But it's that unexpected thing that actually makes astronomy one of the most exciting sciences, because you don't know what's going to come out when you've got this new whiz-bang telescope. So for my guess, I don't know, maybe megastructures, artificial megastructures around other stars. How's that for a just thrown in, just throwing it in as an idea.
That would be amazing.
Wouldn't it?
Yeah.
Especially if you could prove that's what they were, and not just clouds of dust or jade rabbits or things floating around in the universe.
I suspect what we're going to gain from this is more and more and more questions.
Yeah. That's a good answer.
Because of the way this has been planned out and its ultimate goal, we're going to learn a heck of a lot about the early universe and how things tick. But I think that will throw up so many more questions that will then result in more and more study, analysis, papers being written. It's I won't call it a can of worms, because it's not. A can of worms suggests something negative, but I think it will open up, well, maybe Pandora's box.
Yeah, that's right.
That might be it.
I mean, that's a good point, because in a way, excuse me, what often happens is you observe things which don't fit what you had hypothesized. So, like, we have good reason to think that the first stars switched on within the first 100 million years of the existence of the universe. But what if the James Webb fails to find them? That there's no evidence that is the case. Then you've suddenly got you're working in a different paradigm. Where did these stars come from? How did it all kick off? So that's often what does happen, and that's, again, it's the way science progresses. It's building a theory, testing it, revising your theory, testing it again. That whole process.
Yeah. Of course, we'll have all the answers by the middle of the year.
When they switch it on.
What are they doing first? Do we know? What's the first?
I don't know. No, sorry, I don't know. There will be commissioning observations, which will certainly, in themselves, might well start probing, the new regions of knowledge that we expect to come from the James Webb. I'll check up on that. I'll try and find out what their commissioning observations are going to be.
How do they decide what to do? I mean, can Fred Watson put in a submission for telescope time through James Webb, or is that not how it works?
It later on it will be, but not for the commissioning process. But yes, it'll be open access that astronomers will be able to apply for time on it, just as they can with the Hubble telescope.
Fantastic.
If I was clever enough to put in a proposal.
The James Webb, the Fred Watson megastructure study.
Okay. Yeah, all right. I'll try it.
It's happened in the past. People have wanted to use telescopes to look for aliens.
Yes.
They don't look negatively on that, do they, Fred?
They don't if you come with plenty of money to enable it, because that's exactly what the Breakthrough Listen project is. Somebody turns up at Yuri Milner, in fact, a couple of radio telescopes, and buys $100 million worth of telescope time.
Yeah. Wow. Okay, thank you, James. Hope we came up with no answer for you there, because there isn't one yet. Maybe. Let's move on to Northern California.
Hello, Master Nuts. This is Ralph in Northern California again. Love the podcast. Here's an odd question. I'm writing an action-adventure novel with a fair amount of science fiction in it, and I have an aspect I'd like to ask about. I know it sounds unlikely, but then again, science fiction gives license to this kind of stuff. The Lagrange points, they are virtually no gravity points. I'm wondering if it would be possible, as per my story, to do a slingshot effect with the Lagrange point, where spaceships are pulled around an object with gravity in space. But if there was no gravity and they pointed the object or the spacecraft in a certain way approaching the Lagrange point, I guess it would be pulled one way or the other since there's no gravity at that point. Or is it such an infinitesimally small point that it's just impossible to do that? I know that when spacecraft are parked there, they have to be maintained a bit with a little bit of retro action, I guess, to keep them within that area. But it also brought up a point with the James Webb telescope going out to a Lagrange point, how much maintenance that would require.
And that's where Ralph got cut off. So
Yes.
we can only go with what we got. Don't know what happened there, but it's called the internet.
Yeah.
Okay. Good luck with the novel, and let me know when it's done so that I can so I can read it. Would love to see what you've come up with, Ralph. Okay, so the Lagrange point, could you do a slingshot with a spacecraft? What influence does gravity have outside of the Lagrange point? I suppose the question in my mind is how far out of the Lagrange point would you have to be to start feeling the effect of gravitational pull?
Yeah.
I mean, is it a big point? That's a good question that he asked me.
It's so the way to think of it is a gravity well. If you imagine gravity as a sort of, well, the old trampoline analogy. When you're standing on a trampoline, you're creating a well, and for a black hole, that's a very, very deep well. For a Lagrange point, it's not as deep, but it's still a null point. There is a null gravity point there. Excuse me, and it's a combination of the gravitational forces and the rotational forces of the fact that your planets are going around the sun. But I think the answer to the question is no, because with a gravitational slingshot, what you're doing is transferring some of the momentum of a planet, and remember, momentum is mass times velocity. You're transferring some of the momentum of the planet to the spacecraft. And it's that gravitational interaction that lets you do that. Well, a Lagrange point doesn't have any momentum because there's no mass there. It's just a gravitational null point. So I think the answer is no, but it's a really nice idea. One of the other things that's interesting about these slingshots is that I think the rotation of the planets themselves also contributes to the effect, because you get, as I remember, you get slightly different effects depending on which side of the equator of a planet you approach it for the gravitational slingshot. I looked at the details of this a long time ago, and it's all a bit hazy now. But I think you need a gravitating body there in order for it to work, and perhaps even a rotating one as well.
Yeah, Ralph mentioned something that is true about this. The Lagrange point isn't stable. It moves with the movement of the objects that are creating it. Therefore, the James Webb Telescope has to move accordingly. That's
right. So in fact, the James Webb is in orbit around the Lagrange point. So it's and it's because everything's moving. You need to keep it on station, keep it in the proper orbit around the Lagrange point. So that's why, as you said earlier in this podcast, the telescope's got enough fuel for 20 years of operation. That's what it needs it for, to keep it located in the right orbit.
Yes, indeed. All right, Ralph, thank you for your question. We're going to just throw in one more quick one. We're going to the UK this time.
Hi guys, love the show. It's Andy from Eastbourne on the south coast in England here. It's my birthday tomorrow and I'm 56 years old. The question I've got is, how far have I moved through the universe in those 56 years? Be interested to know the answer. Thank you.
Thank you, Andy. Happy birthday.
Yes, happy birthday.
56. It's such a significant age.
It sounds pretty youthful to me, I can tell you.
It's just one of those numbers. 56. Yay. What does that mean? It means 56. How far has he travelled in the universe in 56 years? That's a great question.
It is. And so, you know, a lot depends on what you regard as your standard of rest. In other words, what is stationary in the universe? And because when you think about the way we're moving, there's a number of different ways that we are moving. The Earth is moving around the sun at 30 kilometers per second. So you could work out, 30 times 3,600, which is the number of seconds in an hour, times 24, the number of hours in a day, times 365.25, which is the number of days in a year, times 56. And that'll give you the answer as to how far we've traveled around the sun. But the sun itself has a velocity too, with respect to the galaxy. That our velocity is around about 250 kilometers per second around the galactic center. So you can do the same calculation, but use that. But the one that I think is probably the best one to use if you want to know how far you've traveled in your lifetime.
Let me guess. The Monty Python song.
Yes, that's true. That would do it. That would do it. I've forgotten the name of that song. It's got a proper name. It's a march, isn't it? Is it Liberty Bell? It's one of those Sousa marches.
I was thinking of the one where they say you're standing on.
Oh, that one. Oh, I'm sorry. Yes, that's right.
Rotating at 900 miles an hour.
You're thinking of a different one. That's the Universe song. That's right.
The Universe song. That's
yes,
right.
yeah.
It's good.
It's a great one. And actually, what it says is pretty accurate still, even though that was written 40 years ago or something. But let me just wind this up, because you could say that our most absolute motion in the universe, through the universe, is relative to the cosmic microwave background radiation. Now, that radiation, which we see in all directions, is essentially the flash of the Big Bang. We're looking out into space so far that we're looking back in time to when the universe was still glowing brightly. And we can actually measure our velocity with respect to that. And in a sense, you could say, well, is that the absolute standard of rest of the universe? Well, maybe it is. It's debatable. But the sun's velocity relative to that cosmic rest frame, if I can put it that way, is, wait for it, 369.82 kilometers per second. We know it very, very accurately.
Right.
And so that if you take that 369.82 seconds and multiply it by all the things that I said before to get to how far you've traveled in 56 years, that's the answer. I'm not going to do the sum because we haven't time, but it's a big number.
I think you will probably, Andy, need to get a scientific calculator for this one.
I think just multiplying will do it. It'll just come out with a big number.
Yeah. My calculator usually, when I try to work that thing out, comes up with a big E.
Yes.
E for error. So you can't do it. Too many numbers.
Too big a number, yeah.
But when you do figure it out, Andy, let us know how far you've gone. I will have gone further, of course. A little bit further. Fred would have gone a hell of a lot further.
I knew that was coming. I just knew it was coming. Yeah.
Well, Andy was the one that brought up age.
He did, yeah. Well, I don't have a problem with
Thanks,
it.
Andy. Lovely to hear from you. Hope all is well in Eastbourne. And
I used to live in Eastbourne.
Did you?
Yeah, I did. Yeah. In fact, my elder daughter was born in Eastbourne Hospital.
Well, as soon as you left, Andy found out, and that's why he moved. Dear, oh dear. All right. If you do have questions for us, of course, you can send them to us via our website, spacenutspodcast.com. You can click on the little link on the right-hand side that's sitting on its back. It says, send us your voice message, which is where you can send an audio question, or you can click on the AMA tab, which I'm doing right now, and there you can upload a text or audio question. And while you're visiting, click on the shop link and see what you haven't got that we have, like stickers and tote bags and cups and shirts and everything else that goes along with being a space nut. Get your goodies online through spacenutspodcast.com or spacenuts.io. Thank you, Fred. As always, it's great fun, and we really appreciate you spending time with us.
It's a great pleasure. It's a lot of fun every Wednesday for you and I to get together and do the recording. It's great stuff. Thanks, Andrew.
It is indeed.
Yeah.
All right. Catch you next week, Fred. Thank you.
Yep.
Professor Fred Watson, astronomer at large, and from me, Andrew Dunkley, thanks again for spending some time with us. We look forward to your company on the very next episode. We'll see you then. Bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.